So the next thing we need to look at, there's only two more things we need to look at really, okay? And fortunately the next two things are related, is something called the product rule. Okay, so what does product mean? Sorry? Outcome. Yeah, it does mean that. In maths, does anybody know what product means? It means times. Times two things together. Okay? So in this case, if you have two functions which you're multiplying together, for example, you could have a function which is just effectively made up of two separate functions, like for example, x cubed plus 2, all raised to the power of 2, multiplied by sine of x. Okay? That would be a product of two functions. Okay? One function multiplied by another function. Okay? Then we would have to use the product rule in order to work out the derivative. Okay? So here is how the product rule works. Do you remember when we were first deriving the idea behind differentiation? Okay? So when I gave you just a curve, which was just some function of x, okay, and I said, right, let's find out the derivative at some particular point. Let's say at this point here. Okay, in which case that is f of x. And then the way which we did this was by looking at a change in x and some change in y. Okay, and that change had to be really, really small so that we could work it out at that particular point. Do you remember doing this? Yeah? So then effectively we just looked at a point which was really, really close to it, and then the same in the y direction. So we had a change in x and a change in y. We just divided those two things, dy by dx, and we had then the derivative of the function, the gradient of the function at a particular point. Okay? Now if you think about it, we have now the product of two functions. Now when you visualize product, a really good way of thinking about this is as an area. Okay, so let's suppose, for example, let's just make it a little bit shorter to make it clearer. Let's suppose we have an area which is worked out by the product of two functions. So let's suppose we had one function here and another function here. Okay, so this is another function. Let's make it look like this. Let's say that's g of x. Okay, and again, we work out some particular point over here, which is going to be g of x. And then we have some change in the x direction, some change in the y direction, okay, which then effectively means we have now an area which we're talking about instead of just a single function. Does that make sense? Yeah? So we're now looking at an area because we end up multiplying the two functions together. So I'm going to visualize it like this. Yeah, so let's suppose this is my f of x. So this represents that portion of the region there, or perhaps this region of the region down here. And then g of x could be perhaps represented by this. So the height of the rectangle. Because this is literally what I'm doing. If this is like f of x, let's use a different colour. This is f of x, then this here could be g of x. And because I'm multiplying the two functions together, okay, that's effectively working out an area. Does that make sense to everyone? Okay, I'm working out an area, right? So what I want to do is consider a really small change in each of the respective directions, okay? So I'm going to move a really, really small change in this direction, okay? So that is going to be my change in f, okay? That's going to be my change in f, which I'm going to call df, okay? So I'm going to get change in f in that direction, okay? And I'm then going to consider a really, really small change in the g direction as well, okay? So that's going to be my dg. Okay, if you like, my change in my g direction. And hence I get this. Okay, let me just tie that up a little bit. Okay. So effectively, when I change each of the functions, so I change f and I change g, are you happy now? I get a new area. I get a new area. Okay. And I want to work out what that new area is going to be. Okay. I want to work out what that new area is going to be. So what I'm effectively working out is what is the change, the d, the change, the difference, in the product of the two functions. In other words, what's the change in the area? The product just means the area. Make sense? Yes. Okay. So how am I going to work out this new area? Okay, let me just tie this up a little bit. How am I going to work out what this new area is actually going to be? Good. So I literally need to work out this extra bit. Okay. So I'm going to break it up. I'm going to first of all going to work out this bit up here. What this bit is up here. So it's just going to be my f multiplied by my change in g, okay? So my function, whatever this was originally, my function value, multiplied by my change in g. Let me color code that. Does that make sense? Yeah? But I've also got another bit. I've got another bit over here, which is going to be what? My g function value multiplied by my good. So in other words, what I get is if I want to work out the change in the product of my two functions, I can think about this as f multiplied by the change in g plus this area here, my g multiplied by my change in f. Now, are you happy that I also get an extra bit? I also get this extra bit in here. What's that going to be? Good. My change in g multiplied by my change in f. But let's have a think, okay? We remember when we work out our derivative of our function, we are looking at change which is so small that it's basically zero. Like that difference there is so small that it's basically zero. Likewise, that difference there is so small it's basically zero. That's literally what the idea of calculus is. It's looking at really infinitesimal small change, really, really small change, okay? So therefore, is this area actually going to be that measurable? Not really, no. I mean, this is going to be measurable because we actually have a function value going on here. This is going to be measurable because we actually have a function value going on here. But this is a change in g and a change in f. Multiply the two things together. This is small, this is small. When we multiply it together, it's going to be even smaller. It's going to basically be zero. Does that make sense? So even though there should technically be this term on the end, okay, because it's so small that it's basically zero, we can just basically ignore it. It's just basically nothing. Yeah? So in other words, what I am saying here is that the product, if I have a product of two functions and I multiply them together and I want to find the derivative of them, so I have two functions multiplied together and I want to find the derivative of them, this should be equal to the first function multiplied by my product of g. Yeah? Multiplied by the derivative of g. Plus g multiplied by the derivative of f. Okay? So actually I can make this a little bit clearer by just multiplying through by dx. Let's assume that all of these things are in terms of x. Okay? So I get dx here and I get dx here. Okay? So what I'm literally saying here is that if I want to find the derivative of a product of two functions, that should be equal to my first function left alone multiplied by the derivative of the second function plus my second function left alone multiplied by the derivative of my first function. Okay? This is called the product rule. This is called the product rule. Okay? If you wanted to, I think in the lecture notes I've called f u and g v. So I can quickly just change that, not a problem. So suppose that that is u and that is v. By the way, I'm just writing this as a function. So u has a function of x. U is a function of x. And v is a function of x as well. So now if I just rewrite my product rule, I'm basically saying that the derivative, so in other words, dy by dx if you like, or I could also write that as the derivative of the product of the two functions, that is also fine. Let me color code this. So I could say u multiplied by v. Okay. Oops. That should be equal to my first function left alone. In other words, my u, I just leave it alone. Just take my u, leave it alone. In this case, x cubed plus 2 all raised to the power of 2, leave it alone. Multiplied by the derivative of my second function, multiplied by the derivative of v. So multiplied by the derivative of v. Okay. Plus, then I just do it the other way around. Exactly the same thing the other way around. So I leave my first function alone, my second function alone, in this case it's g, and multiply it by the derivative of my first function. Okay? That would be the product rule. That would be the product rule. Now, if you don't like this notation, that is fine. I can give you more notation. Okay? U gets left alone, and I multiply by the derivative of v. Well, another way of writing derivative is just with a dash. Okay? Plus, well, then it's the other way around. So I'll take v, and I'll multiply by the derivative of u. So u with a dash. Same thing. Same thing. Okay? So let's actually see this in action. Let me write it up in the top right-hand corner. Okay, so I'm basically saying one final time. So the derivative of u times v, okay, the derivative of u times v should be equal to u times the derivative of v plus v times the derivative of u. So let's see it in action with this, okay? So I want to find dy by dx, I want to differentiate. Well, my product rule literally just says I should take my first function, which is just that, x cubed plus 2, all raised to the power of 2, that's my first function, and multiply it by the derivative of v. What's the derivative of v? What's the derivative of sine of x? Cosine of x. And then I should add that to the first function left alone, which in this case is just sine of x. Sorry, my second function left alone, which in this case is just sine of x. And multiply it by the derivative of my first function. So what's the derivative of my first function, somebody? Yeah? Perfect. It's just the chain rule. Just the chain rule. So the power of 2. It's just the chain rule. Chain rule on this. Does that make sense to everyone? Any questions? No? Okay. So I guess we could tidy this up ever so slightly. I can see an x cubed plus 2 hiding in both terms. So I could factorise that out the front if I wanted to. Okay, and then inside the brackets I just left with cos x plus I get 6 x squared sine of x, and that's gone. Okay.